Kánov cez pióny až po mezóny. Veda je všade okolo nás, vítajte pri špeciálnej epizóde Vedátorského podcastu, kde sa spolu s Jozefom rozprávame s Jürgenom Schukraftom. Jürgen je členom komisie ESET Science Award, prišiel teda na Slovensko. Snažili sme sa povychytávať čo najviac týchto výskumníkov, ktorí teraz došli na pár dní, popýtať sa ich na zaujímavosti z ich výskumu. Jürgen Schukraft je senior researcher, čiže taký senior vedec, už vyššie postavený v CERNe, kde pracuje na experimente Atlas, ktorý pravdepodobne poznáte, možno nepoznáte. Bol tam šialene dlho. Bol v podstate v CERNe tesne potom, ako vznikol. Nie úplne v tých prapočiatkoch, ale už tam pôsobí veľmi, veľmi dlho, od 1984. Takže naozaj má v malíčku čo všetko sa v tom CERNe dialo. Samozrejme najväčší úspech CERNu, špeciálne veľkého hadronového urýchlovača, je nájdenie Higgsovho bozónu, o ktorom máme epizódu. Máme epizódy o všetkých časticiach štandardného modelu. Tak sme sa vlastne pýtali, že ako toto vyzeralo, kým sa do toho len púšťali, prečo on vlastne skončil v Európe a nie v Amerike, ako pôvodne plánoval, čo bola vlastne jedna z myšlienok CERNu, stiahnuť ten vedecký kapitál späť z Ameriky do Európy. To sa evidentne úspešne podarilo. Zároveň sme sa rozprávali o budúcnosti CERNu, o tom, že či sa bude stavať ešte väčší časticový urýchlovač, čo od toho očakávame, či boli kredibilné vyhlásenia o tom, že možno objavíme mikroskopické čierne diery, čo si myslí o objavení supersymetrie. Naozaj sme z neho ako experta sa snažili vyžmýkať čo najviac poznatkov o časticovej fyzike a o tom, kam vlastne táto oblasť smeruje. A tak, ak nechcete počúvať epizódu po anglicky, ale chcete čítať epizódu po slovensky, tak YouTube automaticky generuje titulky. Takže ak má niekto problém s angličtinou, tak pár hodín potom, ako je epizóda opublikovaná na YouTube, tak si tam môžete nájsť automatický preklad, ktorý asi nie je úplne dokonalý, ale to je teda lepšie ako nič. Takže dnešná epizóda s jedným z mála, mimochodom, takýchto výskumníkov je veľmi málo v CERNe a tento je jeden z tých naozaj vysoko postavených, Jürgen Schukraft.
Can you please introduce yourself for our listeners in few sentences and tell us about your research and your field of expertise?
So I started off as a nuclear physicist. I did my PhD, it's now 40 years ago, 45 years ago in Heidelberg, Germany. Studying some exotic reactions between what happens when two very heavy nuclei, we used uranium, collide at what we at the time thought high energies, but inside was very moderate energies, to study nuclear shapes and nuclear interactions. And then after my PhD, at that time, the center of good nuclear physics was in the United States. So my idea was to go to Massachusetts. But my professor at the time, he had started to work at CERN in Europe in some much higher energies. And he said, why don't you come by and have a look? And I thought, not really interested. Okay. But anyway, I had some friends. And so I said, okay, I'll come there for a month or two. Mm-hmm. And then I was
There are nice mountains, so at least.
Exactly. So I got stuck, not by the science, not right away at least, but by the mountains and by the wine. France has a good wine, and Switzerland has good mountains, and CERN happens to be exactly in the middle. And so then I decided, okay, maybe not too bad. Let's try it for a year or two. And so I went to CERN. I started looking at more higher energies, more what we in physics also think the higher the energies, the more detailed you look at the matter, the more fundamental it becomes. And so my interest got caught also by the very international flair of the CERN lab. I mean, this is, I don't know whether I should speak about CERN or what I did there.
We'll get there, so.
Okay. So that was how I came actually to CERN, and then I essentially got stuck there.
So this happened 40 years ago?
This happened pretty much 40 years ago.
So congratulations.
Yes. Actually, there are many birthdays this year. CERN happens to have its 70th birthday this year.
Wow.
I'm there. I happen to have my 71st, so I'm 1 year older than CERN. But I spent 40 years at CERN, so doing research.
This might be a slightly implied question, but which particles were unknown when you were starting?
Now, unknown to me or unknown
unconfirmed. So Higgs boson would be one of them, and
W and Zs were not known. Actually, this was the time when quarks started to be taken very serious and turning up in all colors and types at CERN, also in different particles. But not all quarks were known yet. So in the 80s, I don't think the top quark was certainly not known. The bottom quark was known. So one quark was still missing, and the W and Z, so the carriers of force, and of course the Higgs particle was still missing. These are the fundamental particles. And in terms of less fundamental particles, tons were missing. We call them pions, kaons, lambdas. These are then like with Lego stones. You take quarks and you combine them in different numbers and colors and types, and then you can build many, many, many particles. And many of them are still unknown. Mm-hmm. But fundamental particles were mainly those. It was and the graviton, if you like, was not yet observed.
Mm-hmm. So explain why you ended up in Europe instead of United States, but why particle physics instead of something else?
Actually, for the exact same reason they founded CERN right after the Second World War. Mm-hmm. It was the final convention was signed in 1954, which is why we have now the 74th birthday. But it was started around 1949, so really very shortly after the Second World War, with the explicit aim of stopping the brain drain of scientists to the United States, to give them an alternative in Europe. And in order to make an attractive alternative, all of Europe had to work together. No single country could put up something which would have been compatible to the United States. So the original proponents of CERN thought for two reasons: keep the European talent here, but also start again collaborating on the level of states with populations which 5 years earlier were still shooting at each other. So it was always meant to be competitive for science and conducive to peace. So I ended up in CERN 30 years later, exactly for the reason, because it was an alternative which was attractive compared to what was at the United States. So it still works today, and it today works better than at any time. There are more Americans now working at CERN in high-energy physics than in the United States.
Yeah, so it's a huge success story.
A huge success story. Yeah.
So and that's success story for you. And sorry, just why particle physics? And that's when you were starting this, the obvious choice was nuclear physics. So
I started off purely nuclear physics. Then I went for 2 years into really particle physics, meaning there was an accelerator at the time, which actually shut down the week before I came. So it was not working anymore, but there was still lots of data on storage, so I could analyze it. This was called the ISR, the intersecting storage ring, which was the very first collider of protons, so not electrons, but protons. Electron colliders had existed before, but that's the very first. So it was a very important machine, because since then we have built many more colliders. They built them in the United States, they built them at CERN, the next one, the LHC is one of those. But that was the first machine, and there I worked for 2 years really in high energy physics. What I liked was so I said it was the international environment, but also the stimulating intellectual environment. In nuclear physics, if you are 3, you're a lot. If you are 5, you're a crowd, and starting more than 7 in one experiment becomes sociologically difficult. And there I entered an experiment with 100 people, so way above anything. But I liked it because it's very stimulating. You always find people to talk to. You always find people which help you. And you're critically looked at, and you're critically looked at once a week and not once a month or once a year, like for nuclear physics, where there are just less people to interact with. So that I liked. And then after 2 years, I actually combined the nuclear physics and the high energy physics, and we were doing what is called relativistic heavy ion physics.
As a researcher, a particular researcher, are you satisfied with the results that CERN produced, like Higgs boson and so on?
Okay, that's a very wide question. So there are two answers. You're never satisfied in the sense that that's all you wanted to do. There's always more. And you're always satisfied because it's rare that something really doesn't teach you anything. Even if an experiment doesn't work, it teaches you something. Only if you break something that you don't.
So negative results are also results.
Also important. So what and I'm satisfied with CERN. So first of all, I didn't work on the Higgs. So I worked on something else on this heavy iron, which we might speak later about. But you're still part of it, because actually the guys who look for the Higgs, they sit in the next office. And so you meet them in the corridor, and while they will not tell you the hottest secrets, they will tell you already what they are doing and how far they are. And so you're really part of it. So even if you're not working yourself on the Higgs, you're still very close to where the things happen. And clearly the Higgs was a huge success. Now the LHC was built to find the Higgs, and we had a pretty good idea that we would find it. So it was not like switching on, let's see whether we find it or not. Because we did a lot of precision measurements in the previous experiments. And if you measure something with very high precision, often you can extrapolate, so you can look forward what that means for other things. And indeed, the measurements they did with completely different particles showed slight deviations from what you would expect if there's no Higgs particle. And so you could say from our measurements, very likely there's a Higgs and his mass is between 100 and 200 in the units we are using. Actually 100 times or 200 times as heavy as a proton. So that was pretty clear that we knew where to look and what to look for. So in that sense, it was not a huge surprise. It was anticipated that we find it. But it's still a huge triumph, because the Higgs particle is had a very weird history, at least for me, I'm not an expert to the Higgs particle. But the Higgs particle is a theoretical invention. So some 60 years ago in the 60s, we started to have what we would call a unified picture of high-energy physics. Before you had one theory for one phenomenon, another theory for a second phenomenon, and a third theory for the third phenomenon. They were all good, but they didn't know about each other. There were three completely distinct theories, and so starting the 60s, people, and you know that certainly even better than I, because you're a theoretical physicist, started to see commonalities and a common language between all the theories. And it looked beautiful, at least to them. I'm not a theorist, so for me it looked moderately beautiful. For me it looked really daunting. I don't like mathematics, but for them it looked beautiful, and so I believe them. And it could deal with all these things in a common language. It's like if you speak the same language, and suddenly instead of having somebody speaking Slovak and you have no idea what he says, and somebody else speaking English, you have no idea what he says, everybody was speaking the same language. And so the only problem was what theory was telling was nonsense. Nonsense in the sense it made predictions which were manifestly as wrong as it gets. It was predicting that all particles have exactly zero mass. They have no mass.
That's problem.
That's a problem. Because if a particle has zero mass, it does what light does. It runs away at the speed of light. You can't stop. At least in vacuum, you can't stop a particle without mass. You can't go into vessel. And that's obviously pretty wrong. I mean, we were discussing weight, whether we are too heavy or not. And we all know we have a fairly substantial mass. And so that's a problem for a theory. If it's beautiful but wrong, you would say, okay, let's get a better theory. But it was so beautiful that some people thought, how can we save the theory? And you couldn't introduce a mass into the theory, because if you would do it, it would give even more nonsense. So what Mr. Higgs, in his desperation, came up with is, we define math as not what we think it is, but as something else. We outsource math, like we outsource now work. He outsourced math, and he postulated there is a guy who is responsible for math. He called him Higgs. He didn't call him Higgs. He called it, I don't know how he called him. And it has no other job and no other property than generate math. So a pretty weird idea. And in order to generate math for everybody and everything, it has to be everywhere. You see, if there's a particle and this other guy is not around, he has no mass, so he would run away at the speed of light. Okay, so this Higgs particle it had no properties other than generating mass. It had a mass itself also, but no other things. What we know, it had no charge, no spin, no anything, no color. But it generated mass, and it had to be everywhere. That's why some people call it the God particle. It's everywhere, and it's terrible name for everything, but it's a terrible name.
Yeah.
And I actually don't know who invented it. Probably the publisher of the book and not the author, but I don't know.
It sounds like it.
It sounds like it. Anyway, so he said there is this particle. He didn't know anything about it else other than that this guy is responsible for mass by essentially bothering anybody else who has a mass. So it doesn't bother the photon because it still has no mass. But every other particle is sort of bothered by the Higgs particle, and this bothering turns up as a mass. Voilà. So that's pretty crazy, isn't it? I mean, that to me it looks crazy. Anyway, if this beautiful framework should work, you needed the Higgs particle, and so people started looking for the Higgs particle. They didn't know where it appears because there was no prediction. I mean, nothing to tell you how heavy it is. And so we had to measure it. And it was searched essentially in the 60s in all accelerators and all work. But then till we had this detailed measurements at lab, which gave us an idea where it could be, nobody had an idea where it was. So it was looked everywhere before, never found. Until the LHC. So I think that's a big deal. That's a big deal. You make the most crazy prediction you can make for a good reason, and then you ask your experimental colleagues
to be right.
Your problem to find it, and
and they do it.
And they do.
So this was a huge success, but people expected. We are always not satisfied.
Something more. That's why I asked you, are we satisfied? No.
Yeah. So, for example, supersymmetry. It was still being hoped for, yes, but probably not within reach.
So when I before the LHC started, put always a laundry list of open questions which we may have a chance to answering at LHC, and top is always the Higgs, because there we had, let's say, a pretty good idea that if it exists, there are always ways out. So it could have not existed. So it's not like we knew it exists and we just went for the fine. There are always way out to live without the Higgs or something else. But that was on top. But then there was a big list of dark matter, dark energy, extra dimensions, matter-antimatter symmetry, and I don't know how far down it went, but there were. So we do know we have a lot of open questions. Actually, if you measure it in the content of the universe, we know about 5% of the stuff which is there, 95% we don't know. In terms of knowledge, it's probably even worse because we don't even know how much we don't know. Yeah. But at least we know already a few things.
Unknowns.
Yeah. Exactly. So there, I think many people were thinking we would find at least the dark matter. And again, there was actually a good reason for that, because we know how much dark matter there is. And we know, now how did it go? Roughly at which point it might have decoupled in the universe, which then would define how heavy it is. And if you took reasonable numbers for everything that, then you had a prediction. It should be at a mass that would be accessible to the LHC. But that was much less of a clear prediction. But still, it was a clear hint. If it has a certain interaction for which there are reasonable reason, and if it is all of the dark matter, then we should find it we have a good chance to find the LHC, and that we didn't find. We didn't find hidden dimensions either. We didn't find the reason for...
Was there any real hope for those, like creating microscopic black holes, or was this more just a PR stunt?
Let's go down the list. The Higgs was the most likely. Mm-hmm. The dark matter was fairly likely. I mean, if I would have put money on it before, I would have maybe thought the odds are 3 to 1.
Mm-hmm. Oh, okay.
That's not bad.
Yes.
The Higgs, it was maybe, 30%, so not 3 to 1 odds, but 30% probability. Higgs was more like 80%.
Okay.
Dark matter, these are just my random numbers.
Feel free to.
30%, which means very likely.
Nobody will quote you.
That's, let's say, 1 in 100%. And then matter, antimatter, that the CP violation, because that was even less.
Even less.
Because we know it's not part of the standard model, and so you would have to go beyond the standard model. So that
there was a number for supersymmetry. Percent-wise.
That depends strongly on whom you asked. So if you would have asked John Ellis, which was one of the, that's a real unity, maybe you know him. He looks like a theorist. So he has big beard, but a really big beard, white hair, like that.
Unlike me.
And unlike you. He would have put it also in the 10th of percent. I think many other people were a bit more skeptic. But supersymmetry has a very wide range of possible.
Yeah.
Even though already now we are also closing that space a little bit. So supersymmetry, I didn't have a bet. I didn't know what to bet on.
So you said that the thing you like about CERN is there are plenty of people you can talk to about something. You just meet someone at the cafeteria and discuss something. So what is the hot topic now? What are you working on and discussing?
So I'm doing me or CERN?
You.
Me.
You.
Okay, I'm doing something which is very different, but has nothing to do with any of these extra dimension, extra particle. We are studying one part of the standard model, the strong interaction, QCD, so the nuclear force. So that's what's responsible for nuclear energy on one side, nuclear atomic bombs on the bad side. But also the working of stars and everything. So nuclear force is really something which we don't see every day, but it's very much at the core of what is now. The nuclear force is a very strong force. That's why nuclei are very stable objects. That's why you get a lot of energy when you take them apart. But on the theory side, that has a big disadvantage. It's very difficult to calculate. The equations are perfectly well known. They fit not only on a t-shirt, they fit on a tie. So they are much smaller than the equation now. Much smaller than the equation of relativity, maybe at least in terms of size. But you can't solve them. At least not easy analytically, because the force is strong. So you cannot use what everybody else uses otherwise, something called perturbation theory, meaning you make approximations. So you forget about the details, you make sort of a back of the envelope calculation that gives you the bulk. And then you go to the next level and say, okay, the bulk I have, now I look at the first refinement, and that gives me, if I had 90% before, now I'm at 95%. And if I really want to go to 99%, I make 2 more approximations. And that doesn't work with a strong force. If you make your first approximation, you get one number. If you make the second approximation, suddenly it changes by 100%. If you make the third, it goes even negative. So
we have an episode both about quarks and gluons, so people are familiar with the headaches.
Okay,
this is causing.
Okay. So that's why it actually does help to do experiments and then compare that to your calculations. And so what we are doing is we are looking at one part of the strong interaction, which happens at very high temperature. So we are living in a very cold universe, at least compared to the time of the Big Bang. But if you go back in the history of the universe, it becomes hotter. And then there is a phase when all the structure, the complexity of particles and nuclei dissolve into what we call a quark-gluon plasma, a soup where you only have these elementary particles the quarks as the matter particles and the gluons with the force particles. And there's no structure in it. So there are no protons, neutrons, nuclei, no nothing, because the energy is too high, they would melt. And that is really what is thought to be the ground state, the state of lowest energy of QCD. That is, and it has some specific properties, so you don't have complex objects. And good, that's maybe technical. Also, you have chiral symmetry, so mass disappears somehow in this field. So that was a prediction, and we wanted to test that. And as good experimentalists, what you do, you try to create that matter and then measure its properties. So in order to create that, we have to just take a piece of matter and heat it to about 100,000 times the temperature in the core of the sun. And then
only that. Okay.
So that
sounds difficult.
No, straightforward. Straightforward. The way we do it in practice is, so we take lead nuclei, the biggest nuclei we can find, that's lead. There are a few more heavy, but lead is nice and round and stable and easy to get.
And cheap.
And cheap. Actually, our colleagues in the United States use gold, which is about the same.
Just to show off.
Actually, in the quantities you need, it doesn't matter.
They're using their resource budget to the fullest.
So we are good citizens. We use lead. So we have a beam of lead which we accelerate in the LHC. So one beam goes clockwise, the other beam goes anti-clockwise. To the highest energy we can still store in the LHC, and then we collide them. And when two of these lead nuclei hit, then their kinetic energy, so their velocity, is by friction transferred into heat. So you heat them up, and you heat them up so much that everything melts, essentially. So the nuclei melt, the protons and neutrons melt, the energy appears into quark and gluons, and in the end you have literally 10,000s of quark and gluons, so a decent amount of matter, which is the quark-gluon plasma. At least that was the idea. And then, of course, nothing can keep it there. So then, like anything hot in vacuum, it starts to expand and cool and become normal matter again. And that goes into our detector and we'll measure it.
What about the future of CERN? Because there were some politicians that CERN was only for finding Higgs, and after that it's useless. Do you share this sentiment? Or
so
very surprising.
So there can be two reasons why they say that. One is we have answered all questions, so we don't need to do any research, and then they would be right. Or they don't like basic research, and then they would be wrong. Have we answered all questions? By far not. I told you.
Yeah, you told us
there are many questions which we thought maybe we can answer some of them at the LHC, and we can't.
And would bigger circular collider would help in this effort? Or?
So the question is where to look, what to look for, and how to do it. On a time scale which is not unreasonable. So we don't want to do it in 100 years or 200 years, because nobody would be around to do it, because if you nothing do, then people do other things. So what can we do? And of course, with an amount of money which does not sort of bankrupt even the United States, or not to speak of Slovakia or Switzerland. Switzerland could probably afford even more, but
probably.
So that are let's say the framework. So we know there are many questions. Now, most of them, not all, but many of them say, okay, we haven't found these particles at NHC. There's a fairly good chance that we find them once we build better instruments, and that means higher energy and more capable detectors. So that would mean machines, accelerators, which go to higher energy. Now, there are different types of machines with which you can do that. But the only one which currently is practicable is a bigger version of the NHC. There are ideas of using very different types of particles, like even muons. Muons are you think?
Maybe
you're listening.
I think they will.
they will know what I mean.
It has been mentioned once.
Okay. So it's like an electron, just heavier. And it has a big disadvantage for accelerators. It's unstable, so it decays. So unlike electrons and protons, which you can keep in the bottle till you need them, a muon, once you created it, you have to use it very quickly because it decays within millions of a second.
Oh, millions of a second. Okay.
With microseconds.
So it's very hard to work with it.
Exactly. Now that's where relativity comes to the rescue. Because if you accelerate them very quickly to very high energies, then they live longer, at least in their own rest frame. And if you...
So for them, time is
exactly
flowing so differently.
In their own internal framework, they're still
that's amazing.
After a microsecond. But for us outside who don't go with them, they can live, in theory forever if you get them to speed of light. But in practice, they can live minutes. But you have to get them up very quickly because if you don't do, then they are dead by the... And still they decay. So they are very difficult candidates to live through. There are other ideas, but none of them currently you could say that is something with even a time scale of 30 or 50 years you could build already a machine. So the only thing would be a machine with higher energy. There are two other ways one can do it. One is precision measurement. So instead of going to bigger machines and try to create the particles directly, so using all the energy and create them, you can look for indirect effects by measuring very precisely processes which you can calculate. And if there's a small difference between what you measure and your calculation, then you know there are additional ingredients which you need in your theory. So precision measurement. That's how we actually predicted the Higgs already before even seeing it, by measuring certain processes with very high precision, and then we saw differences, and that required the Higgs to be that mass, so that we can do again in principle. So that's another possibility, and that's what they're doing now at the LHC already. Even if we cannot create new particles, we are trying now to measure the Higgs particle and what it does with very high precision. That could tell us already what happens in higher energy. So that's a second approach. So either directly high energy or indirectly via high precision.
So these are the tools, and now you want to ask commission or someone we need 20 billion euros to build this, to start. So you know this is the tool. So what is this tool searching for?
So the answer, it would be what we hadn't answered before. It would be essentially dark matter, dark energy. Maybe not. It
seems to be. We'll leave that for next century.
We'll leave that for the.
But they have something to do.
Or somebody else. Supersymmetry, if still there are viable theories who predict it or not. Supersymmetry is a bit like the Higgs particle. The story of the Higgs. Supersymmetry is a very beautiful theory, because it again makes a common framework, not only for all the different interactions, but it even unites now matter and force, which is a beautiful concept. So that's why some people have a very strong conviction that must be right. Such a beautiful idea cannot be not used. But again, it makes predictions, and if you don't find it. So let's see. So supersymmetry still has a certain space we can look, but it becomes less and less attractive. And then there is still this question of matter-antimatter asymmetry. I'm not sure whether we could address that. I think it's mainly dark matter, which would be now, on my list, the top one.
This will be the next number one on the list.
And supersymmetry number 2.
So from what you said so far, it seems like particle physicists need to be very attentive to details, because you can see the discovery maybe even decades before it's done, just from small deviations. Can artificial intelligence be helpful in this regard, like looking at large data sets and seeing patterns that you'd be missing otherwise?
So at the current level, it's already being used. Actually, we're using artificial intelligence in lower versions as what's called boosted decision trees, and so not ChatGPT, not large language models, but neural networks.
Some detector triggers, or
Do we use them in the triggering? That I'm not sure. I think mainly people use them in the past in the analysis of the data. Because, I mean, as you know, you have to train them, you have to supervise them, I'm not sure you trust them already at the trigger level. Maybe now, I mean, there has been big progress. That has just been... but at the analysis level, we are using machine learning, sort of the more general approach. As was also mentioned this morning in the conference, machine learning we use already quite some time, and it's being used more and more, but not large language model used to write our papers. So that's
but still, is there a chance like you will plug all? It's probably impossible. Plug in all LHC data into a huge artificial intelligence model, and then it will say something like, "Oh, have you noticed that when those electrons are coming at exactly those angles?"
Okay, then you would have really general artificial. Then you would have AGI, general artificial intelligence. Then you would be on the level of a human. Currently, you still have to guide it and say, "Okay, this is what I want you to look for. This is how it should look like. Now you tell me whether you find them or not."
So you have to give exactly.
You have to train. So you train them on Monte Carlo, so on simulated data. Then you or on a subset of your own data. You tell him, this is the signal, this is the background. That's how it looks typically. That's how the other one looks. And now you tell me how many of this and that type you find over in there. So for that we use artificial intelligence. So we don't tell him how to do it. That it does by itself, by the associative learning, but we tell him what to do. If one day you just give him the data and tell him, wake me up tomorrow morning with the discovery so I can phone Stockholm, then we are talking about artificial general intelligence.
So we have to wait maybe 6 more years.
We have to wait.
6 more.
I was discussing here with the people here at ESET, who are much more expert than I. Are we qualitatively or quantitatively different from general artificial intelligence? So is it just sort of scaling it up more and then we are there? Or do we really need more quantum jumps, really something which is even different? So not only gradual better, but really bigly better. They tell me we need quantitative steps. And quantitative steps you cannot time. If it would be scaling, you could say maybe we wait a year or 2 or 5. If we need, let's say, another breakthrough, it can come tomorrow or in 100 years. So that's at least what data. So I'm not an expert in that, but we may have to wait till tomorrow, or
suddenly a new paper, an archive with a good idea, and
or I mean, like the breakthrough in 2010 when they went from the shallow neural nets with only a few layers to the deep neural nets. And that really made all the difference. Then the rest was just applying it, finding some nice algorithms, smoothing them and getting the data through. But that was a breakthrough.
You came to Slovakia in very interesting time because also there are ESET Science Awards and even Nobel Prize. Have you had time to look at the Nobel Prize for Physics?
I read it on the web.
And what do you say about? How did you say that?
Well, it's not really physics, but
I think. The subject, this artificial, is really definitely worthy a Nobel Prize. That's Nobel Prize caliber. Particularly also in the spirit of Nobel. Nobel was not so much concerned with breakthroughs on the fundamental thing. He was actually much concerned about practical things which influence humanity. So many of the first Nobel Prizes were very weird stuff.
Yes.
But so artificial intelligence clearly is a big deal, and it fits very well in the Nobel. My theory is, they said, we want to give it to the Nobel Prize. Now, it's not chemistry, it's not medicine, it's not peace, it's not literature. What's left is physics. That's fine with me.
It sounds like that.
It's fine with me, because actually then I read why they took, and they found a story which you can make sense of. But anyway, it doesn't matter. So
But it's well, the purpose of Nobel Prize is to bring the attention over to science. Maybe should be just spread it a little bit.
Yeah, maybe. Nobel is no longer around, but if he would, clearly I would have a few advices what to add.
I think if he was around, he would add more prizes because it's very difficult to...
For computer science for me, maybe mathematics.
Mathematics would be one.
If you look at the list of field medals and Nobel prizes, it's just impossible to explain.
Anyway, so we live with that, and that's why I think having some freedom in defining, they do it anyway. I think the Nobel Award was here this week, Emmanuelle Charbonnier. She got Nobel Prize in chemistry. She's not considering herself really a chemist.
Yeah. I think she also thinks it's more like medicine or physiology.
Or biology. And there's no Nobel Prize in biology either. So then you have to... Yeah. So, but that's fine. You should not be...
You have to go shortly. So maybe our last question will be, well, you are fulfilling one of the oldest dreams of humanity, to understand the matter around us and what is the world composed of. We have figured out a lot. Still a lot of open questions. So what would be your recommendation for our young listeners? What should be
studying? They should be studying and then go to the fields to research.
You see, so when I had the choice, physics was that was the right choice. That was clearly in the 60s, 70s. There were big breakthroughs. Still, the quantum revolution was what. Whether I would my children today recommend to do physics. Anyway, they wouldn't listen, so...
Well, some of them are listening.
Anyway, I didn't, so I don't have any physicists in the family out of the four. But then some time ago, I found biology. I had really, and still is a very active field. Main thing, neuroscience, consciousness, the brain. That, I think, is one of the frontier sciences. And that actually relates also to computer science. I mean, brain complexity. That I think are... physics still has a lot of interesting, not only high-energy physics, but also solid state. Physics is very wide. But it's not the only game in town. So what I would recommend, actually, everybody should find out what he is most interested in. When I started, actually, I was interested mostly in chemistry when I was little. So I had a little lab and I was doing little experiment because it smelled and stank. And that turned then into physics. So if somebody is interested in archaeology, he should by all means do archaeology. Or if somebody likes the nature around, the things to touch, then physics is the right place. If you like the brain, how does complexity, we had this very nice talk also today, how thought consciousness might rise out of as an emergent phenomena out of something very basic but complex. That is a very interesting subject to look into, a very hard nut to crack. There are science has frontiers everywhere, and the best advice I can give you, choose the direction to which you're passionate about.
I think every time we ask, we get a version of this answer.
And it's
without passion.
I think that's right. You don't become a researcher if you don't love what you're doing. No. If you want to earn your money, that's not a good place to earn money. There are better ways. Lawyer, for example.
For example, yeah. Okay, thank you very much for your time and speaking with us. It was quite a pleasure on our side, and hopefully we will speak in future again. Do you have something to add or something do you want to say to our listeners?
No final word.
Okay, thank you very much and see you next time.
Okay, thank you.
Thank you.
Tak dúfame, že sa vám táto epizóda páčila, ako Jozef bežne hovorí. Viete, ich všade môžete nájsť na lepších aj trochu horších podcastových platformách. Máme web, máme Instagram, sme na sociálnych sieťach, postupne sa snažíme viacej rozbiehať YouTube, máme aplikáciu bez hociakého trackovania, zbierania osobných dát, reklám a podobne, kde si môžete okrem iného aj vypočuť podcasty a posielať nám otázky do fakt dobrých otázok, čo skoro nahrávame ďalšie epizódy a blíži sa aj Vianočná. No a čo? Máme knižku Rozhovory o vesmíre, ak si ešte nečítali, prečítajte si, snáď sa vám bude páčiť a sme radi, že nás počúvate. Majte sa pekne.
Volám sa Barbora Mareková a v denníku SME pre vás robím podcast Ľudskosť o tom, ako na naše mentálne zdravie vplýva rodina a spoločnosť. S odborníkmi a odborníčkami rozoberám, ako sa v rodinách dedí trauma a ako sa dá v dospelosti uzdraviť. Ale rozprávam sa aj s ľuďmi, ktorí vyskúšali terapiu a zaujíma ma aj celospoločenský pohľad, ako sa menia slovenské rodiny alebo ako sa v našej spoločnosti cítia Rómky, Rómovia či ľudia, čo sú queer. Poďte sa učiť spolu so mnou, ako lepšie rozumieť sebe, ale aj ľuďom okolo nás. Podcast Ľudskosť vychádza každý štvrtok vo všetkých podcastových aplikáciách.